So example number 4, differentiation of parametric equation. You'll be told to find the equation of a normal drawn to the rectangular hyperbola. X is equals to 5t, y is equals to 5 over t, and t is equals to 2, isn't it? Now, for you to determine the equation of a normal, all you need is the gradient of the normal and the known point, isn't it? And for you to determine the gradient of a normal, you must first of all get the gradient of the tangent, because the gradient of the tangent is from the derivative of the curve, isn't it? So you must get the derivative of the curve. That is when you are able to determine the gradient of a tangent, isn't it? And that is when you will be able to use the relationship between perpendicular lines to determine the gradient of a normal. Are you together there? So, the first parametric equation you've been given, x is equals to 5t. So, at a point when t is equals to 2, from this, at a point when t is equals to 2, what is the value of x? What is x at a point when t is 2? 5 times 2. You get x to be 10. We are done with that. Then the next thing, x is a function of t, meaning we can differentiate x with respect to t. So if you differentiate x with respect to t, you get dx over dt. If you differentiate 5t, you remain with 5. Then dt over dt is silent, isn't it? You are done with x. Are we together? We go to y, the parametric equation. The other side will be given y is equals to 5 over t. And you know 5 over t is the same as 5 times t raised to negative 1. Means it is in the numerator, isn't it? Are we together? So we want y at a point when t is 2. So what is y when t is 2? That is 5 over 2, isn't it? You get 2.5, isn't it? And you can see very well y is a function of t, isn't it? So you can differentiate y with respect to t. So if you differentiate y with respect to t, you get dy over dt to be, this is in case of a polynomial, negative 1 times 5, negative 5. Then you reduce the power by 1, isn't it? Are we together? So if you reduce the power by 1, you get negative t raised to negative 2, isn't it? But t raised to negative 2 is the same as over t squared, isn't it? Now from here, we now want the gradient. This is the derivative. So what are these derivatives? At a point when t is 2, you can move with that or you just get to the derivative direct, whichever step which looks simpler to you, okay? So we know that the derivative of the curve is given by dy over, you are differentiating y with respect to x when we are using the rectangular form, isn't it? Or the Cartesian. So from there, y is a function of t, x is a function of t. So what is the implication there? We divide both numerator and denominator with the dt. So y, if you divide by dt, what you do in the numerator, you also do in the denominator, isn't it? So it means dy over dx is the same as dy over dt divided by dx over dt, isn't it? Are we together? Are we together? Yes. So what is dy over dt? Negative 5 over t squared divided by, are we together? So we have negative 5 over t squared divided by 5. So from there you will see 5 goes with 5. If you simplify, you get negative 1 over t. You get negative 1 over t squared, isn't it? Are we together? So that is the derivative of the curve. But you want the derivative of the curve at a point when t is 2. So you come and ask yourself, what is this derivative when t is equals to 2? You get the answer to be where there is t, you put 2. So negative 1 over 2 squared, you get negative 0.25. Negative 0.2. So you found that is negative 0.25. So you know the derivative of a curve at that point is the gradient of the tangent, isn't it? It's the gradient of the tangent. But we need equation of a normal, meaning we need the gradient of the tangent, isn't it? Of the normal, isn't it? So you know the gradient of the tangent m is the derivative of the curve at that point, isn't it? So what is the gradient of the normal? So gradient of normal, if we say the gradient of normal is m1, then it will imply the gradient of tangent by gradient of normal is negative Because normal is perpendicular to tangent, isn't it? Are you seeing that? So that means, that implies, what is M1? -1 divided by gradient of the tangent, isn't it? If you divide both sides by this, you remain with the gradient of the normal, isn't it? So -1 divided by -0.2? 25. Would you get to be the gradient of the normal? You get it to be 4, isn't it? So the gradient of the normal is 4. Have you seen the way we found the gradient of the normal? The derivative of the curve is the gradient of the tangent, but the normal is perpendicular to the tangent, isn't it? So the gradient of the normal by gradient of the tangent is giving you -1. So the gradient of the normal is -1 divided by gradient of tangent. Is that okay? So we have the gradient of the normal and we have one known point. So you can see from these two, we have one known point. We have a known point xy, and one known point is, what is your known value of x? X is 10 at t is equals to 2. We found x to be 10, isn't it? And we found y to be, the y is 2.5. So our known point is 10, 2.5, isn't it? So for us to get the gradient, the equation of the normal, we simply compare the known gradient with the unknown, isn't it? So change in y is y minus y. You get y minus 2.5 over change in x is x minus x. You get x minus 10, isn't it? So this is how to determine the gradient, isn't it? So this gradient of the normal, we found it is equivalent to 4, which is the gradient of the normal. So what you do is just simplify. So if you simplify this, you get x minus 10 goes to the other side, you remain with y is equals to, so if you take it here, you get 4x minus 40 plus 2.5. You should be very fast in working out that. I can see this -37.5. What have you found? Some of these things can only be seen. You don't even need to do them. X minus 10 going to the other side, that is 4x minus 40. So then -2.5 going to the other side is plus 2.5, isn't it? You get -37 point. So this is in the form y is equals to mx plus c, and you've actually determined the equation of a normal given the parametric equation of that rectangular hyperbola.